Morning, everybody. We are going to start what is quite possibly my favorite part of all of physics. So you're going to have to forgive me for going on too many tangents. And I'll do it, but I apologize in advance. Too much detail on some things. My graduate work was in optics. My master's thesis, part of my master's thesis, is still orbiting the planet to this day. It's all a part of really a question that has been around for a very long time. And so to begin optics, I want to build a bridge. I want to build a bridge to everything that we have done in this course so far, electric and magnetic fields, into optics and light and everything that's going to happen with that, which is then going to carry us into modern physics and quantum mechanics, okay? So there is a question that drives basically all of scientific pursuit, predating Newton, predating chemistry, predating like the modern sciences. It's a question that I think was asked when we were sitting around campfires and drawing on cave walls. It's a question, it's very like, it's in your face, it's always there. Sometimes it's something we think about, sometimes it's not. And it's a very simple, deceiving question. And that question is, what is light? Like what is this thing that comes from the sun? What is this stuff that comes out of our light bulbs, right? But before, and spoiler alert, I'm not going to be able to answer that question completely for you, okay? No physicist can, because we're still grappling with the implications of asking that question. Asking that question gets you into electric and magnetic fields. It gets you into quantum mechanics. It gets you Einstein and Witten and others who came along and just started altering our concept of how the universe is put together and how it works. We're gonna try. So for the rest of the semester, we're gonna try and answer that question: what is light? Okay. But we're gonna start with simpler questions, right? Questions that maybe we could answer, like, how do you make light? Like, come on, how do you make light? What do you do? Yeah, you push a button, right? Okay, right? You just turn the switch and it goes on, Mr. Balogh. What's the big deal? So somebody mentioned like burning or heating something up, right? At its very basic, a campfire, right? Like think about that, right? Our species' ability to make fire on demand changed our world, right? It's all been downhill from, no, it just, like the amount of technology that we were able to do to cook our food, all those, beat back the darkness and the night, right? Okay, we make it by heating things up. Like in its basic form, a regular everyday light bulb, one of those old-fashioned, old-timey light bulbs with the filament in it, it's just a big resistor, and you send enough electricity through it, it's going to heat up. And you can feel the warmth coming off the bulb. That's infrared light. We can't see it with our eyes, but we can definitely feel it with our skin. Same thing goes for the campfire. The sun, right? The sun is a big nuclear explosion going off constantly, right? And if we shut off the sun somehow, we are in big trouble, because where does everything on the planet get its energy from? The sun. Okay, I'm a scientist. I got to be more accurate. What does everything on the surface get its energy from? Because there are certain bacteria and stuff that can live off of the nuclear decay that's going on in the Earth's core. But like most of what we would call life nowadays is utterly dependent on the sun, right? For growing the plants that the carnivores eat, then we eat the other carnivore. The chain is there, right? So in short, right, we make light by burning things, by heating things up. And we can feel the energy coming off of it in the form of heat, but we can see it also with our eyes. Here's another question, actually, that's pretty simple to answer nowadays. And it's fairly well known what the speed of light is. It wasn't always that way. Originally, natural philosophers and proto-scientists, like in the age before Newton, they assumed light had infinite speed. Like light was just sort of everywhere all the time. And Fizeau and others, Romer, you don't have to remember any of these names, but like they whittled away, okay, at the issue of how fast does light go, and we're able to start measuring it. And nowadays we have very modern techniques, right, to be able to measure the speed of light. It's like we round it 3 times 10 to the 8 meters per second. The actual number is like 299,000 something, something, something. It's a number, so I can never remember, right? We use the symbol lowercase c, 299,000, blah, 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 whatever it is. And we usually shorten that in physics to 3 times 10 to the 8 meters per second, okay? That's the accepted value for the speed of light. And it's a universal constant. You go anywhere in the universe, that's what the speed of light is in a vacuum. Or air. Air is pretty close to vacuum as far as light is concerned, okay? So we were able to answer 2 questions almost right away. How do you make it? How fast does it go? But what it is, right? This is a Pandora's box. This is a can of worms. Those are all phrases to suggest that, yeah, you can ask a simple question, but you better be ready for the answer, right? Or where the likely answers are going to take you, because it's going to take us from one end of the universe to the other. It's going to take us from the very smallest quarks that make up the nucleons of atoms all the way up to the largest structures of superclusters of galaxies. It's going to encompass everything, just absolutely everything. Now, sometimes I get a question, Mr. Balogh, you're giving us a history lesson, because really this is going to sound a lot like a history lesson, right? Okay. What am I on the hook for? What are you going to test me on, right? That's the golden question every scientist or every student wants to know, right? So in answer to that, starting now, I'm going to expect you to know, like, I think it's fair game on an exam to ask you a question, like who thought light was a blah, 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 or what experiment did somebody do? I will never ask you dates, right? I will never say, what year did blah, blah, blah discover the blah, blah, blah? I don't care, right? Okay. Although I'm going to contextualize it and put it into time, right? But if you're taking notes, I would write down like major player, right? Isaac Newton's a major player, right? Like every name I throw on the board for the next 15 minutes, you're going to want to write down. And then you're going to want to have some idea of what they believed light was and like what did they do? Like experiments or ideas did they put forward to kind of promote their ideas. So to give 2 very rough categories, and you need to understand that these categories, they are well, basically physicists don't have much of an imagination, and so we divide the universe into 2 things, okay? In the universe, there are particles, okay? Or there are waves. Like everything in the universe is one or the other. Think of a baseball, right? What's a baseball? Particle or wave? Particle, okay? What is, when you go to the ocean, you're looking at the stuff in the water. What are they? Waves. So like what's different about particles and waves? Size? I can get waves the size of baseballs. That's not a problem. Shape? Yeah. What do you mean by shape? I mean, it's kind of obvious, isn't it, Mr. Balogh? Like waves wiggle, right? Right? Do baseballs do this? No. right? And so the key difference between particles and waves come down to like what they can do and their behaviors. And there's 4 phenomena that physicists use to kind of decide, right? And we're going to go over these phenomena a lot. We're actually going to dedicate whole chapters of the textbook to things like reflection and refraction, that kind of stuff. So the 4 phenomena, and I'll repeat these over and over again. You can write them down right now if you want, but we'll get to them. Reflection, refraction, interference, and diffraction. Now those are all kind of big words, okay? Reflection's pretty easy. If I take a tennis ball and I throw it at the wall, what's it going to do? It's going to bounce, isn't it? Right? That's a reflection. Okay? The ball encountered a change in medium. It was in air. It encountered a solid medium, the wall, and at that interface, it bounced off. Okay? Refraction is the bending of the path of something when it tries to change medium. So like if you've ever tried to throw, like skip rocks on a river or a lake or something like that, right? If you don't get the rock thrown just right, it won't reflect off the surface, right? A skipping rock is a reflection off of the surface, right? If you don't get it right and it goes into the water, well, you maybe never carefully looked at it, but the rock changes its direction when it enters the water, right? It doesn't go in the same path that you threw it, okay? It actually just kind of slows down really fast and goes somewhere else. So refraction is a change in direction that is caused by moving into a new medium. So reflection, right, you can't get into the new medium. It just bounces off, okay? But refraction is you've entered, your medium has changed, the thing you're traveling it has changed, the properties of the thing you're traveling it has changed, and now the direction that things are going to change. So the way you remember which one's particles and which one's waves, particles can do the 2 R's. They can reflect and they can refract. Okay? Maybe I'll write those words down for you on the board. Like I said, we're going to refer to these words a lot. Okay? Okay, they can reflect and they can refract. We also say refraction, right? Adding the ION suffix. All right, waves, they can do both of the R's. Okay? I'm not going to rewrite them. Okay? But they can also do something called interference and diffraction. And we're going to talk more about these things later. Okay? Interference, simply put, is the superposition or the putting together of 2 things in exactly the same place at the same time. Particles can't do that. You cannot put 2 baseballs at the same place at the same time. If you try to do that, they'll bounce off of each other. They can't occupy the same space. Anybody that's ever tried to walk through a door and missed the handle, right? You're so confident, you're seeing that person you're really interested in, and then you flub the door handle, right? Embarrassment ensues. If you try to get through the door without pushing the handle, you know that you can't be at the same place at the same time as the door. It's like physically impossible. So particles cannot do this thing we call interference. This isn't pass interference like in football, okay? This is actually overlapping in space and time. But waves can. Sound waves can pass through each other. Light waves can pass through each other. Any kind of wave can be at the same place at the same time as another wave. Diffraction is the bending of a wave around an obstacle or through an opening. Again, I'll discuss that in a lot more detail when we get to that chapter. But one way that you know that something is a wave is if it interferes and diffracts. It's definitely a wave. Can't be a particle. Okay? Particles, right, can do the 2 R's. So the 2 R's in and of themselves are not enough. Okay? It's that interference and diffraction that really allows you to tell the difference. Okay. So what do we got Isaac up here for? As sort of the father of physics and the one that started the modern scientific revolution, Isaac Newton weighed in on what he thought light was. And now, I'm greatly oversimplifying history, and some of the stories I'm going to tell you aren't strictly true in the sense that this is exactly what happened. I'm altering some of the narrative and changing some of the people around, but the actual essence of the story is the same, right? I just don't want to get into too much detail because there was too many people involved. But we know and understand Newton from his laws of motion and like gravity and stuff, but he actually spent a lot more of his scientific time talking about light. He published Optics, right? This grand book all about what light was and what it did and how lenses worked and all that sort of stuff. And Newton came down on the side, okay, of light being a particle. Isaac Newton took a look at the evidence of reflection and refraction and used it to show that light was particle in nature. Now, one of the big things about waves is that they need a medium in which to travel. You can't, waves like sound waves don't exist in space. Why not? There's no medium. There's no material for the sound waves to propagate through. However, you can be in space and throw a baseball, no problem, right? Particles don't rely on the material they're traveling in to exist, right? But waves do. And so Newton argued that light comes from the sun and it has to go through the vacuum of space. So it can't possibly be a wave. Because to be a wave, it has to, there's medium dependence. And so he looked at reflection, he looked at refraction in great detail and said, you know what, light must be a particle. And he coined a term, he called it the corpuscular nature of light. Those of you studying medicine know what corpuscles are, any of that kind of stuff? No? Haven't gotten to the medical terminology class. Okay. A corpuscle is a portion of, is it the bloodstream? Okay, it's one of the things that exists on a, am I getting that right? Is it it's part of the blood cell? It's a Latin term, okay, that refers to little piece of or little chunk of. And so he coined this term. Today, we give chunks of light a different name. What do we call pieces of light? Individual little chunks of light coming off of things? Photons, right? That term would be coined around the time of Einstein. So Newton comes down very much on the side of light's a particle. Okay. Like what kind of weight does Newton carry in the scientific world? Like, yeah, like all of it, right? And the man was a jerk. He was ruthless. He was like the Elon Musk of his age. Anybody that disagreed with him, he canceled them. Like he used his power and influence to like destroy their lives scientifically, personally, like he was just a bad guy. And so we shouldn't venerate him for any of that. But his scientific ideas really formed the groundwork for everything that we can use today. It's the scientific equivalent, forgive the spiritual reference, okay, the biblical reference, but it's kind of like Moses wandering off the mountain saying, hey, there's 10 things I really think we should look at here. When Newton says something, that must be the way it is. It's Isaac Newton, right? And so for a good 70 years, nobody really questioned this idea about the nature of light. If Newton says light's a particle, light must be a particle. Problem solved, right? He solved the rest of the universe. This must be it. And so it would take a new generation of scientists after Newton's death, because now they're not worried about him coming after them, right? To start pushing against that narrative, right? And this, you got to understand, is a little bit like career suicide if you're a physicist, right? You're going out to prove Newton wrong, right? This is not a good starting place, okay? Especially since Newton's laws and gravitation, all this kind of stuff is just paying so many good dividends, right? Enter onto the stage, pun intended, a young man who in 1805-ish, would start pushing against Isaac Newton's ideas. And Thomas Young was a British experimental physicist. I'm an experimental physicist, so I've got a soft spot for experimental physicists. But he started doing experiments with light. And what Young discovered, okay, and we're going to go into more detail. You're going to understand what these pictures look like in a second. What Young did is he took a light. They didn't have light bulbs at the time, so he used sunlight. He put it on this thing called a double slit. He did something called the double slit experiment. And on the other side of this double slit, he got a pattern on the screen, shadows and bright lines that can only happen when two waves are interfering with each other. We're going to go into detail in this a couple chapters from now, right? But the point is, Thomas Young has experimental evidence that light is interfering with itself. What can particles not do? They can't do interference, okay? And so Thomas Young is in a little bit of a problem, right? He has experimental evidence that Newton was wrong. Or at least light's doing something that isn't particle-like. And so Thomas Young actually publishes, right, all of this, okay? And he's quoted, so even before his experiments and really becoming sort of public with these results, he's writing to people. He's published, in letters, scientific correspondence, people asking him what's going on in your lab. He's saying things like this. Look at the language that he is using here, right? He uses the word retard. Today we use that as a slur against somebody, but what does it mean to retard something? To slow it down, right? And notice, he's saying, I venerate Newton, I appreciate what he did, but we kind of have to look and acknowledge that he was liable to err, old-timey speak for he can make a mistake. How dare you say that the great Newton could make a right? But this is kind of how science works and moves forward, right? In spite of the egos involved and Newton having to prove that he's right even when he's wrong, science and scientific process and experimentation wins out. And Thomas Young is sitting on the smoking gun, the experimental proof that light is acting like a wave. Now, I wish I had time. Okay, I'll tell this story very quickly. I'll try as quickly as I can. Thomas Young went to the Paris Academy of Sciences. Paris Academy of Sciences was ground zero for all things science, turn of the century, 1800s. So this is 1805, 1806. And Thomas Young is addressing the world's scientific elite. Everybody who's anybody in the scientific community, basically in Europe, has come, right, to the conference, the yearly conference of physics. And Thomas Young stands up and starts telling everybody that Newton's wrong, right? Well, the scientific establishment is not having it. They're squirming in their seats, they're starting to get uncomfortable, and then the unthinkable happens. You don't do this at a scientific conference, but this is exactly what happened. A gentleman by the name of Simeon Poisson. That last name means fish. That has nothing to do with the story. I just think it's funny. Stands up, middle of the lecture, 300 people in the room, right? Stands up, clears his throat. 300 sets of eyeballs swivel around. What the heck is going on? And right there, Poisson starts telling Young how wrong he is. You don't do this. This this is a breach of etiquette and rules and common decency and like what? But Poisson wasn't having it. He's like, look, this can't be, blah, blah, blah. So, and Thomas Young, like younger guy, right? He hasn't barely established his career. He's up there and he's got like the big guns of Simeon Poisson staring right at him, right? And 300 other people with angry, right? You're telling us Newton's wrong. All looking at it, but Thomas Young stands his ground. He's like, look, I've got the experimental evidence. You're welcome to reproduce the experiment if you want. I'll show you how to do it. Poisson's getting like angrier and angrier. Okay. So this is like Victorian times when two gentlemen have an argument and you really just we can't agree to disagree. There's one answer. What do? What? You duel. It makes perfect sense, right? We're going to prove who's right by shooting each other. It's supposed to be an enlightened age, right? We kind of haven't gotten past it today. But these are the kinds of things that I never have time to tell you about in any of our lectures. I'm letting it all out right now, okay? I'm letting all the history happen right now, okay? Because yeah, it's a story. What does it have to do with the science? There's a part of science that is so important, and those are the humans that are behind it. You have to understand that they were flawed, they were brilliant, they were dumb, they were great, they were bad, like all of the entire spectrum of humanity, right? Scientists are no different, right? But sometimes it's just too juicy. You just can't get past the story. And so now, okay, so Poisson and Young are starting to get to the point where it's time for a duel, but they are scientists, right? So instead of going out into the street and shooting each other, which isn't going to help anybody, okay? What do they do instead? Knives. No, they propose a duel of experiments. Thomas Young's double slit needs to be verified. Other scientists need to do it to make sure he wasn't, smoking dope or doing something wrong or whatever, right? Okay? So more than one person needs to be able to replicate it and show that the same thing's happening. So there you have on one side Thomas Young's double slit experiment. Poisson, right there in the meeting, proposes an alternative experiment. He's like, all right, Young, if you think you're right, then not only should light interfere if it's a wave, but it should also diffract. So I, Simeon Poisson, propose that we take a very small, this is a much enlarged version of this, right? But a very tiny metal ball, okay, that you shine some light onto, okay? Diffraction is the bending of a wave around an obstacle. So if light diffracts, then I, Simeon Poisson, say that the light will bend around the sphere, rays from the top will bend that way, rays from the bottom will bend that way. The rays will meet somewhere on the backside of the sphere, right, where there's supposed to be a shadow. I, Simeon Poisson, believe that spot will not be there. They pause the conference. Everybody runs out, starts setting up equipment. It didn't happen that. It took them weeks. But anyway, right? They do the experiments. Thomas Young's experiments get verified. Poisson's experiment that he proposed and never did, other people did it for him. Because he was like, this is trash. It's not going to work. You guys are wasting your time. Others went and did it. And to this day, this spot, which did appear, is called Poisson's spot. Why is it called Poisson's spot? Is that some sort of like spiteful hater, we're going to dunk on this guy because he was wrong? Why? How do you get something named after you in science? Be the discoverer. In this case, Poisson was the first person to propose the correct theoretical explanation for why this spot would exist, right? And so he's given the credit for something that he believed wasn't going to be there, because he believed so strongly that light had to be a particle. Poisson wasn't an idiot. Newton wasn't an idiot. Like, they had valid concerns for why light could not possibly be a wave. Again, this whole the sun thing, right? Like light moving through the vacuum of outer space. There's no medium for the waves in which to travel. So how do you solve that problem? Okay? We're going to get to it in a second. But sort of simultaneous to all this going down, and I haven't really, it's so hard. It's so hard to really impress upon your minds how momentous this moment was for science. Because you now have a schism, you have this divide that takes place. Most scientists are still on the side of Newton, right? Light is a particle. There's a small but growing body of scientists that are like on the Thomas Young camp who are saying light is a wave. And there's arguments back and forth. There's name calling. There's vitriol. It's like a soap opera, right? But science is like in crisis, right? Because you've got these two competing explanations for what light is, and we seem to have evidence for both. What are you going to do? Well, in the midst of all of this argumentation, time goes on, right? It's been about 50 years later. Black and white photography is invented, right? This idea that you can now capture a moment in time on a piece of glass that's coated with some silver nitrite and some other things, right? The daguerreotype and the other black and white photo, like this would change how we record things, right? And so artists are running around trying to take pictures of things, but scientists are like, ooh, new technology, I'm going to go play with it. And so they start investigating the nature of light, right, with this new technology, okay? And so scientists developed ways to let very small amounts of light into the camera. They could control. Nowadays, back then they couldn't do this, but nowadays we can control it on a per photon basis. Like we have the technology to say, I just want one photon, boop, right, okay, to go into that camera. But back then they kind of had to, they were dealing with other issues in their technological acumen. But when you let a small amount of light into a camera, and it doesn't matter if it's a digital camera or a film camera. So this has nothing to do with chemical reactions or anything, okay? When you let a small amount of light into a camera, this is what you see. Can you tell what this object is yet? Not really, okay? But here's the earth-shattering truth. If light is a wave, every wave carries all the information about the wave in it. So small amounts of light would be waves with very small amplitudes, but all of the information about where the light came from, what it's doing, is in that wave nature. And so what you should see is the entire image, but very faint. And that's not what happens. What happens? Dots. Which one of these two is dots? Not all the information's there. It's coming in chunks. If you let a little bit more light in, more dots appear, right? And so you get more of the picture. Now we can see that it's what? Like a face. It's a human face, right? And then if we let even more light in, okay, then we get the whole picture. But the bottom line is that the whole picture was made up of dots. This is film. You can do the same thing. This is a digital sensor. It's in reverse though, right? Just a little bit of light, some more light, and then finally all the light. And this test pattern here isn't a face. It's just a gradient right in the center going out the outside. It's a good way to test digital light sensors. But as you can see again, right, it's independent of the chemistry or anything. The actual physical nature of light is being captured by the camera. And it leads to only one conclusion. This is direct experiment. We picture it didn't happen, right? It's happened. What is light? So you may not be aware of it, but simultaneously to all of this story that's going down about light, Michael Faraday is going, hey, there's some interesting things about electric fields over here and magnetic fields and all this stuff, right? Okay, it's simultaneous, right? It's like for science, it's like almost like all of science kind of started in 1805, right? Like the amount of acceleration of light and knowledge and discovery just takes off after 1805, 1815, somewhere in there. So the people who are in the light is a wave camp. And again, we got problems now because we have actual experimental evidence supporting particle nature, and we have actual physical, scientifically validated evidence of the wave-like nature of light. And the big problem that has to be solved is, what do you do about the sun? What do you do about the vacuum of space? If light's a wave, how does it propagate through space where there's no medium? Well, scientists did what every self-respecting scientist is going to do when confronted with an impossible situation. You invent something. You just make something up, okay? And the thing that the scientific community who believed in the wave-like nature of light invented or made up was something called the luminiferous ether. It was called ether theory for short, okay? And ether theory stated that throughout the universe, there was this ether. And this ether was the medium through which light traveled. Now, the ether, obviously, you can't see it. You can't taste it. You can't touch it. You can't feel it. But it must be there. Right? Because obviously it is, because light comes from the sun and it gets to the earth, and we know light interferes and diffracts, so there must be a medium. We just have to go find it. And some of the best minds in all of experimental physics did just that. They would spend until like 1920, 20 years after it's 40 years after it's been disproven, okay? Spoiler alert, ether doesn't exist. They would invent machines, experiments, that were 100,000 times more accurate than they needed to be to detect the presence of the ether. And over and over and over again, they would not find it. The scientist's last name, his name was Robert Millikan, and he worked at Case Western Reserve University in Ohio. Foremost among the scientists chasing the ether. On his deathbed, he would express regret that he never found the ether. That he considered it one of the chief failings of his career. That somehow maybe he didn't build his devices well enough. And that it had never been found. He died thinking that the ether was there. When in fact, Millikan showed us through hundreds of experiments the null result. It's called the greatest null result in all of physics. He went looking, and others like him went looking, and they never found it. It's super hard to prove something is there or not there when all the evidence you have is that nothing happens. Okay? The null hypothesis, the null result, is well known in science. It's very, very difficult to prove. On a personal note, my sister and brother-in-law work at Case Western Reserve as professors and deans. My sister's the dean, my brother-in-law is the professor. And I went and visited, first time I went to visit them at their new place at Case Western, and 2 decades ago. And my brother-in-law was showing me through he's a biologist, he's all the biology labs. And I was kind of bored. He's like, well, let me take you over to the physics labs. I was like, I've seen physics labs, it's okay. You know. He's like, no, I think you might like this. And so he walked me into the physics building. He knew it was there, and he knew my love of experimental physics. And I walked into the lobby of the physics building, and sitting right there in the lobby in a glass case was Michelson's original interferometer, the device that he was using to chase the ether. And I just stopped, and I started crying. And I just stayed there for 2 hours. And I kept taking selfies, and I made my brother-in-law take pictures of me crying over the instrument. Like that was the thing, right? That I'd heard about all of these years. And read the life story of Michelson and all that kind of stuff, and there it was, the instrument that he had worked so hard to try and prove the ether was there. One day in college, I was in senior level electricity and magnetism, my 4th year course, where we start doing all of the stuff we did for the whole beginning of the semester, but we do it over 2 semesters. Like imagine having to do electric and magnetic field like in nauseating detail with no simplifications or anything. Dr. Spencer was our teacher, and Dr. Spencer would come in, and the room was a little bit like this. It was about half the size, but he would come in, and it had boards on all 4 walls, and he'd start at this board, and he'd start writing, right, in the course of a 45-minute lecture, and he'd keep writing, okay, and we would, judge how difficult the lecture was by how many times he went around the room, right? Because he's over here and we're still copying stuff down over there, right? And he'd get to the other wall and he'd start erasing at the same time that he was writing. Like literally, he was like, and we're like, right? And he's like, God, keep up, right? Dr. Spencer was amazing, but oh my gosh, was that class hard, okay? One day he comes in, and instead of starting on that board, he walks to the front of the class, and he stands there and he says, today I'm going to prove to you that the ether exists. And we're like, we know this story, Dr. Spencer. You can't, no. He's like, no, I'm going to prove to you that the ether exists. And we're like, are you okay? Like, do we need to go get somebody? He's like, no, watch. He started right here. He didn't start in the corner. He started right here, okay? And he started writing and deriving and doing all the math of the ether and all that kind of stuff. And it took him only about 15 minutes, and he got to right about here. About here, we were convinced. Hook, line, and sinker, we wanted to believe. It was beautiful. It was elegant. It answered all of the questions. Couldn't do your taxes, but that's different. It was amazing theory. Just incredible. And it answered so much in such a small, compact little space. And he got to here and he said, that's it. Too bad it doesn't exist. Dropped his chalk in the tray. It was the best mic drop I've ever seen in my entire life. And walked out the door and left us stunned, emotional wrecks. Because we had glimpsed absolute beauty and perfection. We wanted to believe because it was much easier than everything he's been dragging us through. But it had one big problem. And what was its problem? Didn't exist. Yeah, it just didn't exist. Over and over and over again, experiments could never, ever find it. But there is an answer. And it comes in the form of a Scotsman who rocked an amazing beard. This is James Clerk Maxwell. You pronounce that word Clark if you're Scottish. James Clerk Maxwell arrived on the scene, okay? And in his brief life, he only lived to about 50-ish. Don't panic. You don't have to know any of this math. In his brief scientific career, not only did he fix the ether problem, but he described 70 years before we were even able to take a look, James Clerk Maxwell described correctly how the rings of Saturn formed. He solved problems in thermodynamics that were making people's ears bleed from how difficult they were. He did it simply and elegantly. I dare say he was a theoretical physicist on the level of Einstein in the decades before Einstein. We kind of point to the 1900s as saying that was sort of the century of Einstein, right? The premier. There were other physicists doing amazing things, but everybody remembers Einstein. The decade of the 1800s, that had people like Faraday in it, right? Like big names. James Clerk Maxwell was the Einstein of that century. Absolutely incredible, the things that he did. And one of the things he did is he brought together everything that was understood about electricity and magnetism. Michael Faraday couldn't give mathematical expression to his ideas. He lacked the formal mathematical training to do it. He was a brilliant experimenter, a brilliant ideas, imagination, could visualize all these things. Maxwell took Faraday's visual ideas and put them into the mathematical language that physicists could understand. And so in a very real way, we credit Maxwell with basically explaining to us Faraday's genius, okay? Maxwell would correct one of these equations. This term right here, which I know doesn't mean very much to you in this form, but this is a correction that Maxwell would add to this summary of everything about electricity and magnetism. And that correction would be the reason we now call these equations Maxwell's equations. As a physicist and a teacher, I feel it is my job to make sure everybody who ever comes through my classes sees this at least once. Because there's something about these equations that you need to understand, and it's not the math, okay? It's what the math points to. Believe it or not, so these are written in a form of mathematics called vector calculus. It's the most common form of Maxwell's equations. You know you've made it, okay, when Maxwell's equations you can buy on a t-shirt from Etsy or Amazon, okay? I've seen tattoos of Maxwell's equations. I've seen coffee cups with Maxwell's equations on them. I was in Edinburgh, Scotland 2 years ago, which was the birthplace of James Clerk Maxwell. I went and visited the place he was born, and I saw the Maxwell Institute. I was in seventh heaven, right? And I was crying and all that kind of stuff. But I get emotional over the strangest things. But I was walking down the streets of Edinburgh, Scotland, and I practically ran into the James Clerk Maxwell statue. There's statues of lots of people in Edinburgh, but one of them's of James Clerk Maxwell. And there's no sign that says James Clerk Maxwell was awesome dude, blah, 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 right? Okay? All it had on the plaque were these, right? For the people who know, you know. For everybody else, it's gibberish. And what is it that physicists see when they look at these equations? Get your calculators out. I want you to do a calculation for me. Get your calculators out. It can be your phone or something, doesn't matter, okay? But get your calculators out. When Maxwell summarized and organized all of this stuff, he discovered something incredible about electric and magnetic fields. In his math, and I love this derivation. It's my favorite derivation of all physics, but I'm not going to bore you with it. He discovered a constant floating around in his calculations, okay? And that constant was 1 over the square root of mu naught times epsilon naught. Now, we've seen mu naught and epsilon naught before, right? Do you remember epsilon naught? It was a number, it was a constant associated with the electric field. Like if epsilon naught's there, you know the electric field is here. Now it's pretty easy to see there's an E here for electric field, right? But like epsilon naught, electric field. And what was mu naught associated with? Magnetic fields, right? It's the constant associated with magnetic. So what is Maxwell discovering? Okay, the first equation, believe it or not, has Coulomb's law in it. It doesn't look like it the way we did it, but like it's called Gauss's law, and it tells you that electric fields start and stop on charges. Just trust me on that. That's what that math says. The second one is Gauss's law for magnetic fields, which tells us that magnetic fields form closed loops. I know it says equals 0, which usually doesn't get you anywhere, but this gets us everywhere in terms of the distinguishing feature between electric and magnetic fields is that electric fields start and stop. Magnetic fields go around in loops. This one right here, okay, is something that we call it Faraday's law, right? And we've been studying it a lot, okay? But basically, EMF is hiding over here, and we've got a changing magnetic field, changing magnetic flux on this side. This one right here is called Ampere's law, again, which we didn't do in this class, but it's basically like Faraday's law of electromagnetic induction, but for magnetic field. So I said that kind of wrong. It's like Gauss's law, but for magnetic fields. Anyway, that's not important. What's important is Maxwell put together all of these equations, and this constant fell out. So what is this constant? So mu naught is 4 pi times 10 to the minus 7 in SI units. Okay, I'm not going to write down all the units. Epsilon naught is 8.85 times 10, is it minus 12? Minus 12. Okay, also in standard SI units. Okay, so what I want you to do is I want you to put this into your calculator if you haven't already, right? You got to multiply mu naught and epsilon naught together, and then you need to take the square root of that answer, and when you're all done, invert it, 1 over it, right? 1 divided by that number, right? Has anybody gotten it yet? Yeah, I got it. What'd you get, Truman? 2.9986. Keep going.
3380.5.
What is that? Speed of light. Maxwell has discovered the speed of light in some equations that involve electric and magnetic fields. Dynamic electric and magnetic fields that self-propagate through the universe. Maxwell has discovered light as a wave in the electric and magnetic fields. No medium required. Because of Faraday's law and Ampere's law, if magnetic flux is changing like it does if magnetic field is a wave, then coming along with it is an electric flux, an electric field that is also forming a wave. The change of one field causes the change of another. That's what these equations are saying. And so when a physicist looks at these equations, we see math, we understand the math, but like what we see is a wave moving at a very specific speed, a constant speed for a vacuum. And that wave is light. No medium required because the medium is electric and magnetic fields. When I look at these equations, I see an explanation for why the sky is blue and why clouds are white and for why rainbows show all of those colors, for why color happens in the first place, and how those colors can strike the retinas of your eyeballs and my eyeballs and make it as an electrical signal to your brain. I see a reason for DVDs and Blu-rays. I see a reason for flat panel display. I understand the physics that governs every electrical circuit and every electrical impulse in our bodies, from why we feel things. Remember Coulomb's law, the fundamental law that governs all forces between charges? It's all in here. All of it. In 4 equations. This is one of like the holy grails of physics. Our drive, not just our job, but like the thing that moves a physicist along is this crazy idea that the universe can be explained simply. Not that the math can be simple. This math is horrible. Remember Dr. Spencer going around the room, right? Okay. But the fact that we can describe everything we know about anything that involves electricity and magnetism and light in 4 equations, just 4? You don't need any others. This is it. That, for a physicist, is beautiful. That, for a physicist, is elegant. That, for a physicist, is simplicity itself. We are after understanding how the universe works in its most basic and simplest terms. Notice those words do not mean easy, but they do mean that we can boil every complex interaction that we see into very simple fundamental ideas for how they work. It is a magnificent result that we are going to spend the next 3 weeks trying to come to terms with. Because Maxwell didn't just discover light as we see it. He discovered the entirety of the electromagnetic spectrum. Every single wiggle in an electric and magnetic field gives rise to the technologies you see up here and other things. How many of you like your internet and your wireless, get data anytime, anywhere, right? On the surface of the planet. I mean, I, as a person, try to find places where this doesn't work, and that's my happy spot. But like, to be able to not have a wire connecting this to the wall, that used to be a thing. Yeah, I grew up talking to my friends, twisting myself up into the cord, and then untwisting myself, right? Okay? So I'm old, right? But like, from being able to keep us safe at the airport to not cutting ourselves open to let the demons out, but to be able to see into the structures of the human body without ever having to cut them open, that's incredible. We live in Star Trek. Like, seriously. It's incredible. TV broadcasts, all kinds of radio, X-rays, gamma rays, every broadcast that goes Wi-Fi, anywhere, at any frequency. This is the electromagnetic spectrum. The part that we see with our eyeballs, this incredible universe that we perceive, is such a narrow, teeny, tiny part of this entire family of electromagnetic radiation. When a physicist says light, we don't mean the stuff that we see with our Mark I eyeballs, right? We're talking about the entire thing. And it's incredible, and it's amazing, and it's going to take us places that you can't possibly imagine yet. Well, maybe you can. Depends on how much of the book you've read. But what Maxwell establishes, and what we are going to spend the next 3 weeks dealing with, is the fact that light is a wave. Now, today, I've given you theoretical and experimental evidence for both camps, right? Okay? Put a pin in this discussion. Not so much a discussion as a lecture, isn't it? Because we're going to come back to it. This is going to come back. 3 weeks from now, 3.5, we are going to come back to this very position, having understood as much as we can about Maxwell and optics and light and all this kind of stuff, okay? Because there's another person that we need to talk about. But not yet, right? Not yet. We'll get to him, okay? So, let's dig in to... So that was all of the story, and believe it or not, I needed you to have context for what we are about to learn. The context and the story behind our drive for understanding what light is cannot be understated. And I wish, if I was not allowed to teach physics anymore or science at all, my next favorite subject would be history. Not because I like historians or anything, but because I love telling stories. And I can make the dullest history sound awesome. I just made a scientific conference sound exciting. I have talents. Maxwell's equations, I showed you, right? But we need to, there's all that, right? Okay. But let's figure out what these electromagnetic waves are, right? And all those kinds of things. So this is going to borrow a little bit from Physics 2A. In Physics 2A, you did sound waves. You did wave mechanics, masses on springs, harmonic motion leading into waves, all that kind of stuff. So we do, since we're talking about waves again, we kind of have to remember some stuff about waves. And don't worry, I got your back on this one. So let's get this out of the way, right? So waves have wavelength. I don't know if we remember our wavelength or anything about waves. But if you've got a wave, okay, so apparently this is a nice innocent sine function right here, okay? The wavelength, does anybody remember what it was? The distance. Yeah, it was like crest to crest or trough to trough. Pick two identical like places on a wave, like two peaks, two troughs, whatever, right? And the wavelength was the distance between them, right? And we use the Greek letter lambda for that. To draw lambda, you draw a candy cane that's falling over and it sticks out its leg to catch itself. Okay? That's how you're supposed to draw. Like it's supposed to be more of like sort of like anyway, like a coat hanger. But anyway, I just draw a candy cane and a leg sticking out. Most physicists do that. So there's the wavelength. There is a velocity at which these peaks or troughs move. Okay? That velocity, of course, measured in meters per second. The wavelength measured in meters. And when it comes to waves, there is like kind of a master equation that is the relationship between wavelength and frequency. Is any of this sounding even vaguely familiar? Little tiny bit. You probably forgot the details, which is okay. I'll remind you, right? Okay. The equation in the box is a trap, and you need to know it's a trap. And if you were never taught it was a trap, I'm teaching you now that it's a trap. It's a trap. it is not an equation about velocity. Because the speed of a wave, this is going to be very important moving forward, the speed of a wave is determined only by the medium in which the wave is traveling. I'll say that again, I can't give it enough emphasis. Does the velocity depend on the wavelength? No. Does the velocity depend on the frequency? No. How do you change the velocity? Change the material or medium that the wave is moving through. Do sound waves travel different speeds in water compared to air? Yes. Why? Because the medium changed. The properties of the medium changed. Okay? So this equation sometimes traps people because they say, oh, well, if I make the wavelength bigger, the velocity will go up. That is not what happens. Speed of a wave is determined by the properties of the material that the wave is traveling in. We shorten that by saying it depends on the medium in which the wave is traveling. This equation is all about the relationship between wavelength and frequency. If V is a constant for whatever material you're in, and the wavelength goes up, gets bigger, what happens to the frequency? It goes down. Wavelength and frequency in this equation are inverses of each other. Solve for one of them, right? You'll end up with V divided by the frequency or wavelength, right? The other side will be frequency or wavelength, and you'll see that they are inversely related to each other. So, what does a wave look like that has a shorter wavelength? What do we have to do to the peak to peaks? We got to bring them closer together, don't we? Okay. So our wave would look something like this, wouldn't it? Jeez. It thought I was trying to erase. So those peaks, and I can't draw to save my life, but you get the idea, right? How many peaks per time would you see if this wave were going past you? More or less than the top wave? It's definitely more, right? Do you see how there's like more in the same amount of space, right, that's taken up? So this one has a shorter wavelength, right, but a higher frequency. This one's frequency is lower, okay? Frequency is like counting the number of peaks that go by you in a certain amount of time. And the unit of frequency is hertz, Hz. It's an inverse second. Again, this is all kind of like we're pulling this out of 2A with our wave mechanics because now we're going to start talking about waves. So we kind of have to have some of these definitions in our back pocket. Now, for electromagnetic waves specifically, okay, we're going to replace that speed with the speed that we know electromagnetic waves travel at. What speed do electromagnetic waves travel at? So we usually write this equation as C equals lambda F. Okay? Meaning that it's the speed of light, right? And so the wavelength of that light and that frequency of that light are inverses of each other. If the wavelength gets bigger, the frequency gets smaller. If the frequency goes up, the wavelength goes down. They're yin and yang. Okay? And again, that brings us back to the electromagnetic spectrum. And you'll see on here, okay, that they've given wavelength and frequency. Don't worry about wave number and electron volts, okay? But frequency on the bottom, wavelength on the top. Like, as frequency goes from 10 to the 5 to 10 to the 21 hertz down here on the bottom, right? Your wavelength is going from 10 to the 3 meters all the way down to 10 to the minus 12 meters, right? So again, they're inverses of each other. And we will talk about the wavelength of like visible light. Well, visible light has a wavelength. So this actually depends on the textbook and the physicist you're talking to. I like to go from 400 to 700 nanometers because those numbers are kind of easy for me to remember. Some physicists would say 350 nanometers to 750 nanometers, but like that's really pushing the ability of eyeballs to see stuff, okay? So my expertise lies in optics, and this is what I say, and this is generally what physics textbooks tend to go with. There's a little bit of argument based on human biology, but that's squishy stuff, and physicists don't. This physicist doesn't get into squishy stuff. So those are all wavelengths. Nanometers. What's a nanometer? Yeah, that's a 10 to the minus 9, isn't it? Okay. So again, those prefixes are going to be in there. Okay. You'll be asked to find like the energy that light carries. Okay. So let me just dump some equations on you that make calculating these things pretty simple. That's a big capital U, which is our general symbol for potential energy. You can find the energy of an electromagnetic wave, of a light wave, okay, by either doing that epsilon naught times the maximum electric field squared, or by doing 1 over mu naught times the magnetic field squared. So either way, okay, you can find, and what units would this energy be in? Joules. It's an energy, okay? So the amount of energy that's hitting your skin from these light bulbs, right, is being carried by the electromagnetic waves and being imparted to your skin. It happens to be a very low amount of energy and not bad for you in the sense of, well, let's say ultraviolet light. Where do we get most of our ultraviolet light exposure from? The sun, okay? Ultraviolet light sails right through our atmosphere. It's not blocked by the atmosphere very well. It does a little bit. But what is it about ultraviolet light and its transfer of energy that is so dangerous? It causes what? It causes our skin cells to sacrifice themselves to protect our more squishy bits on the inside. That's a long technical way to say that you get a sunburn, right? A sunburn is literally the top layer of your skin sacrificing itself, dying so that the lower layers aren't given problems. Now, if you stay out too long, you know sunburns can hurt, right? And of course, too many sunburns, depending on your complexion and how much myelin, whatever it is you got in your cells, blah, 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 can lead to skin cancer, all kinds of stuff. So does the frequency and wavelength like matter in terms of health effects? Sure. But in terms of just energy, all you really need to know is what the electric field and magnetic fields are. And you can calculate the energy of any light wave. And we'll get more into shortcuts for calculating that. By the way, to get between the electric and magnetic field strengths, all you need is the speed of light. It's a handy way to get back and forth. I'm going to show you the demo, so I don't have to bring the demo equipment back, but I'm mostly out of time. So I just want you to see this so that I can then refer to it when we get back together and calculate how we polarize things. Polarization is another one of those proofs of the wave-like nature of light, because what I'm about to show you is impossible to do with particles. Polarization is forcing any wave, but light in particular, to wiggle in only one direction. Okay? So I have this overhead projector. I still like overhead projectors. I think they're amazing. But We don't use them anymore. So I put a polarizer, that's what this is. I put a polarizer on the overhead projector. What's the first thing you notice that the polarizer does? Like the light here compared to the light there. It darkened it, right? As a matter of fact, it cut the intensity by 50% exactly. Okay? Light has an infinite number of degrees of rotation, okay, for the wiggles that are coming at you. So the electric field could be coming at you vertically or horizontally or anything else all the way around the circle, okay? That's what unpolarized light is. And so this is unpolarized light. This is polarized light now. And in polarization, the first thing that you do is you knock out 50% of the light, because light on average is 50% vertical and 50% horizontal coming at you. It's everything in between, but like statistically, you can just line them all up, 50% vertical, 50% horizontal. So what we did is we knocked out 50%. And all of the light in this polarizer has now been forced to be vertically polarized. Okay? So this light's unpolarized, but this light is only vertical. We've wiped out the horizontal stuff. If I come along and I stick another polarizer on top, do you notice how not much changes? Like, I can kind of set it. You see that it's like a little bit darker, but it's not 50% darker. The reason it's a little bit darker is because these are made out of plastic, and plastic is imperfect, and I can't get, perfect transmission through materials. But if I take the top polarizer and I change its transmission axis, so both of these are now vertically oriented, and I start rotating my polarizer, what happened? The first polarizer got rid of the horizontal and made sure that only vertical was going through. The second polarizer at 90 degrees to the first says that only horizontal can come through. Well, if the first one makes only vertical, how much is left for the horizontal? 0. I have literally canceled all of the light passing through. What's more is I can dial in. Do you see that? I can dial in exactly how much light I want to have come through depending on the rotation of my polarizers. We'll do the math for this next time, but what you have just seen is the demonstration of determining whether or not your sunglasses are polarized. If you suspect that the little hut in the mall is selling you a story and those aren't really polarized lenses, what do? Grab another pair. Same identical pair. Hold up one sunglass, 90 degrees to the other. If you put those lenses together, what should happen? It should blacken out if they're polarized. If they're not polarized, you hand them back very nicely to the person and say, "You're lying to me." Right? Okay. Got to be nice. Even if you do want to shove the sunglasses in places where the sun doesn't shine. All right. I will continue on with polarization, and then we will move into chapter whatever it is. 25? Because this was 24? I don't know. We'll start with the next chapter next time on Thursday. I will see you then.